Good afternoon, all, and you are welcome to today's class. Today's class is study section 3, which is probability. What are the objectives of today's class? The objectives of this unit is to introduce students to foundational concepts of probability theory, which are essential for analyzing uncertainty and making informed decisions based on likelihood. By the end of this unit, students will be able to 1. Understand the concept of a random experiment and how outcomes are defined within a sample space. Explain the axiomatic definition of probability, including the basic rules and properties that govern probability theory. Differentiate between types of events such as independent, mutually exclusive, and conditional events. Apply the rules of conditional probability and compute probability involving dependent and independent events. Evaluate real-life and theoretical problems involving mutual exclusive events and use Venn diagram to visualize relationship between events. And the last but not the least is develop the ability to solve fundamental probability problems using appropriate formula, logical reasoning, and structured method. Learning outcomes for study section 3. The learning outcomes for study section 3 are 1. Define and describe a random experiment, including the key terms such as outcomes, sample space, and events. Explain the axiomatic approach to probability, which include the 3 fundamental axioms and their implication. Differentiate between the types of events, which are the simple, compound, independent, dependent, mutually exclusive, and exhaustive events. Compute the probability of an event using logical, empirical, and axiomatic methods. Apply the formula for conditional probability and use it to solve problems involving independent events. And then identify and test for the independence of 2 events using probability rules. Recognize and analyze situations involving mutually exclusive events and correctly apply the addition rules of probability. Solve a variety of real-world and theoretical problems and interpret probability value in context and explain what they imply about the likelihood of an event occurring. Introduction. What is probability? Probability theory is a branch of mathematics concerned with the analysis of random phenomena. Probability defines the likelihood of an event occurring. That is, probability tells us how often some events will happen after many repeated trials. There are many real-life situations in which the outcomes of an event is predicted. Probability theory is widely used in various fields, which include statistics, finance, physics, and gambling, to name just a few. It helps us make predictions, assess risk, and make informed decisions in situations where there is uncertainty. By understanding and utilizing probability, better understanding and navigate the uncertainties of the world around us. What is a random experiment? A random experiment is an experiment that can result in different outcomes, even though it is repeated in the same manner. Random experiments, it results in different outcomes, even though it is repeated in the same manner. For example, when we toss a coin, it can either be, it can bring any value. It can bring either 1, 2, 3. It results in different outcomes, even though if we repeat them in the same manner, we toss a coin the same manner and it can bring out different outcomes. That is what probability, a random experiment is. Another example is a die. When we throw a die, it's either head come, tail come. Even if we throw it in the same manner, the result in different outcomes. Now, sample space. What is a sample space? A sample space is the set of all possible outcomes of a random experiment. A sample space is the set of all possible outcomes of a random experiment. It is denoted by symbol S, capital S, or omega, or sometimes U. For example, tossing a coin. When we toss a coin, it either give us head or tail. When we throw a die will either give us 1, 2, 3, 4, 5, 6. Another example is measuring the weight, gives x given x containing r. And also take note that each individual outcome in the sample space is called sample point. A sample point. A sample point is each individual outcome in a sample space. It's called a sample point. For example, when we throw a coin, when we toss a coin, is either head or tail. If it is head, it's a sample point. If it is tail, it's a sample point. So a sample point is the individual outcome in the sample space. The sample space provides foundation for defining events. Those events that we define as the subset of the sample space. That leads us to an event. What is an event? An event is the set of outcomes of an experiment that forms a subset of the sample space. What is an event? An event is the set of outcome of an experiment that forms a subset of the sample space. E.g., when we throw a die, our sample space will be 1, 2, 3, 4, 5, 6. Event A can be rolling an even number. What is the probability that an even number will come? Which is 2, 4, 6. If we see 2, 4, 6, it will be subset of the sample space 1, 2, 3, 4, 5, 6. Another event, let us name it event B, which is rolling odd number. What is the probability that when we throw that die, it will give us odd number? We have the odd number, it can either come bringing 1, 3, and 5. So the event is 1 for rolling odd number will be 1, 3, and 5, which is also the subset of the sample space. So an event is the set of outcome of an experiment that forms subset of the sample space. Also, another example is a tossing of a coin. Our sample space can either be head or tail. Event A can be the probability that head will come, and event B can be the probability that tail will come. But the sample space of throwing a coin is head and tail, while the subset, which is event, is either head or tail. So event is the subset of the sample space. Now, they can ask us what are the difference between sample space and event. Sample space, it is the set of all possible outcomes of a random experiment. Sample space is the set of all possible outcomes of a random experiment, while an event is the subset of the sample space. Another difference is every outcome that can possibly happen is included in the sample space. Every outcomes that can possibly happen is included in the sample space. While event, it includes one or more outcomes that are of interest. Events include one or more outcomes that are of interest. Another one is sample space is the universe in which event occurs. Sample space is the universe in which events occur. While an event contains multiple. If the event contains just one outcome, it is called simple event. And if the event contains multiple outcomes, it is called compound event. Let's go to axiomatic definition of probability. The axiomatic definition of probability was introduced by Andrei Kolmogorov in the year 1933. It provides a rigorous mathematical framework for probability based on three axioms. Now, the axiomatic definition of probability: a probability function is a set of functions with domain, which the domain is algebra of events, and the counter domain with interval 0, 1, which satisfy the following. Or we can say the axiomatic definition of probability is: a probability function B is a function P of f given 0, 1, assigning a probability to each event, which satisfy the three listed below Kolmogorov axioms, which are the axioms of non-negativity, the axioms of normality, and the axioms of additivity. They have three axiomatic definitions, which are axioms of non-negativity, the axiom of normalization, and the axiom of additivity. Now, let's talk about the first axiom. It says, for any algebra contained in an event, probability of A is greater than or equals to 0. Or you can also say, that is, what does this imply? Probability of A greater than or equals to 0 for all contained in the algebra, which means probability can never be negative. It can be either 0 or greater than 0. That is axioms of negativity. Probability can never be negative. It can be 0 or greater than 0. The second axiom is axiom of normalization. Axiom of normalization, that is, the probability of omega, or the probability of sample space, is always equals to 1. Probability of sample space is always equals to 1. Probability of the entire sample space, when we add all the sample space together, their probability is always equals to 1. The probability of the entire sample space is 1. Something in the sample space must happen. Axiom 3, which is additivity for disjoint events. Additivity for disjoint events. If A1, A2, A3 up to AN is a sequence of mutually exclusive events in algebra, and if A1 union A2 is equals to, this I ranges from infinity to 1, which is contained in algebra, then probability of the union of AI must be equal to summation of a probability of AI. That is, the probability of the union of the disjoint events equals to the sum of their individual probability. So therefore, from these three axioms, many useful rules in probability can be derived. They are derived. Such rules are: the probability of an empty set is equals to 0. That is, the probability of null is equals to 0. If A1 and A2 are mutually exclusive, probability of A1 intersection A2 is equals to empty or null. They don't have anything in common. Also, probability of A1 union A2 union A3, where AI intersection AJ is equals to empty or null. Also, probability of A1 intersection A2, probability of A1 intersection A2 is equal A2 intersection A3, and A1 intersection A3 is equals to null. So probability of A1 plus A2 plus A3 is equals to summation of the probabilities of AI. Now let's go to conditional probability. Conditional probability is the probability of an event occurring given that another event has already occurred. Conditional probability is the probability of an event occurring given that another event has already occurred. What does it answer? It answers the question, what is the probability of an event A happening if we know that event B has already happened? Now, let A and B two events in an algebra of a given probability space. The conditional probability of A given B is denoted as probability of A given B, which is equal to probability of A intersection B over probability of B. Example, a batch of 500 container of frozen orange juice contains 5 that are defective. 2 are selected at random without replacement from the batch. What is the probability that the second one selected is defective given that the first one was defective? From these questions, we can see that both oranges selected are acceptable. So the selection is without replacement. Please, let's take note. The selection is without replacement. Let A denote the probability that the first selection is defective, and let B denote the probability that the second selection is effective. So they are now asking, so what is the probability that the second one selected is defective given that the first one was effective? So we have probability of B given A. From the question, from the example, our n is 500, which is a batch of 500 container of frozen orange. From here, our n is 500. Number of defective is 5. So probability of 1 is defective without replacement will be 5 over 500 times 1 minus the probability, is without replacement. So if you take 1 from something, it will remain 4 over 1 minus total, which will give us 499. So the probability that 1 is defective without replacement is 5 over 500 times 4 over 499, since it is without replacement, which is equal to 0.018. Okay, number of acceptable. They say 5 are defective, so we take away 5 from 500, which will give us 495. So number of acceptable oranges is 495. Then they say probability that both are acceptable without replacement. Both oranges are acceptable without replacement. It will be 495, that is the number of our acceptable, over 500 times 1 is defective without replacement, which will be 4 over 499, which will give us 0.98. Then probability that both are defective. Probability that both are defective, it will be probability that both are acceptable without replacement plus probability that 1 is defective without replacement. Probability that both are defective will be probability that both are acceptable without replacement plus probability that 1 is defective without replacement, which is 495 over 500 times 499 plus 5 over 500 times 499, which will give us 0.0181. Another example on probability, they say a ball drawn at random from a box contains 6 red balls, 4 white balls, 5 blue balls. Determine the probability that the ball drawn is red, the ball drawn is white, the ball drawn is red or white. Probability that the ball drawn is red. Way of choosing a red ball over total way of choosing a ball. So the way of choosing a red ball is 6 over total way of choosing a ball is 6 plus 4 plus 5, which is 6 over 15. That will give us 2 all over 5. Probability of white will be 4. The balls way of choosing a white ball is 4. So it will be 4 over 6 plus 4 plus 5, which will give us 4 over 15. Also, probability of choosing blue is 5. Way of choosing blue, probability of choosing blue will now be way of choosing a blue ball over total way of choosing a ball. That will be 5/6 plus 4 plus 5, which will be 5/15. That will give us 1/3. Then probability of not red. It is not red, then it will be 1 minus probability that it is red. Probability that it is not red will be 1 minus probability that it is red. That will be 1 minus 2/5, which is equals to 3/5. Probability of red or white will be way of choosing a red ball or a white ball over total way of choosing a ball. Probability of red or white will be way of choosing a red ball or white ball over total way of choosing a ball, which is equals to 6 plus 4/6 plus 4 plus 5. That will give us 10/15, which is equals to 2/3. Or probability of red or white, that will be 1 minus probability of blue, which is equals to 1 minus 1/3. It should give us the same answer as 2/3. Also, if 3 balls are drawn successfully from the box of the above questions, find the probability that they are drawn in order red, white, blue if each ball is replaced and not replaced. Probability that red, white and blue will be probability of red times probability of white times probability of blue, which is equal to 6/6 plus 4 plus 5. That's the probability of red, times 4/6 plus 4 plus 5. That will be probability of white, times 5/6 plus 4 plus 5. That will be probability of blue. Then probability of red with replacement, if replaced with replacement, then without replacement will be 6/15. When you add it together, probability of either blue, red, white or blue will be now be 6/15 times 4/15 times 5/15, which will give us 8/225. Now we have dependent event. When we say an event is dependent, what do we mean? Dependent events are 2 or more events where the occurrence of one affects the probability of other. That is, if one occur, it will affect the probability of other. Dependent events are 2 or more events where the occurrence of one affects the probability of other. 2 events A and B are dependent if probability of A given B is not equal to probability of A. Example, if 3 balls are drawn successfully from the box of the above questions, find the probability that they are drawn in order red, white and blue if each ball is A replaced and B not replaced. Solution: if each ball is replaced, then red, white and blue are dependent events. Let me repeat again. If each ball is replaced, then red, white and blue are dependent events because the occurrence of one or more events where the occurrence of one affects the probability of the other. Because say dependent events are 2 or more events where the occurrence of one affects the probability of other. So if each ball is replaced, then R, W and B, red, white and blue, are dependent events. So probability of red, white and blue will now be probability of red times probability of blue times probability of white, which will give us 8/225. Then B question say if each ball is not replaced, then probability of red, white and blue are dependent events. So see, probability of red, white and blue will now be probability of red times probability of white times probability of blue, which will give us 6/6 plus 6/15 plus 4 times 4/15 times 5/15. That one will give us 8/225. Then C, probability of red, white and blue if they are replaced with probability of red times probability of white times probability of blue, which is 6/6 plus 4 plus 5. Then we do for red, white, and we do for blue. That will give us 6/15 times 4/15 times 5/15, which will give us 4/19. If each boy is not replaced, then red, white, and blue are dependent events. So we estimate for that. That also will give us 4/19. Then independent events. Two events are said to be independent. That's the opposite of dependent. If the occurrence or non-occurrence of one does not affect the probability of the occurrence of the other, then they are independent. Otherwise, they are dependent. Two events, E1 and E2, are said to be independent if the occurrence or non-occurrence of E1 does not affect the probability of the occurrence of E2. Then probability of E1 given E2 is equal to probability of E2. Then E1 and E2 are independent, otherwise they are dependent. Example, tossing two coin. When we toss two coin, the sample space we have 4, which are, is either our sample space will be head, head tail, tail head, or tail tail. Then assuming we divine our event to be event A if head comes, event B if tails come. So probability of A, that is event A will open, that is if at least a head will come, will be head, head tail. Probability of B, tail, we shall see one tail, will be either head tail or tail tail. Then probability of A intersection B will be 1/4, which either we see head and tail, just one head and tail together, that will be 1/4. Since probability of A intersection B is equal to probability of A times probability of B, A and B are independent. Then another one is the mutually exclusive event. Two events are said to be mutually exclusive events if the occurrence of any of them excludes the occurrence of the others. That is, events that cannot happen at the same time. They are also called disjoint events. Thus, E1 or E2 are mutually exclusive events. Then probability of E1 E2 equals to 0. If E1 plus E2 donates the event that either E1 or E2 or both occur, then probability of E1 plus E2 is equal to probability of E1 plus probability of E2 minus probability of E1 E2. Therefore, probability of E1 plus E2 equals to probability of E1 plus probability of E2. That is, two events A and B are mutually exclusive if A intersection B equals to empty file, or B intersection A, or probability of A intersection B equals to 0. Example, sample space, assuming we throw a die which give us 1, 2, 3, 4, 5, 6. We define our event A is rolling an even number, which is 2, 4, 6, and our event B is rolling a odd number, which is 1, 3, 5. These events are mutually exclusive because they do not share the same outcomes. You can roll both an even or an odd number at the same time. So since there is nothing common between event A and B, A intersection B will give us null, which is empty. Thanks for listening.